Good morning, good afternoon, good evening, whatever the case may be. We are back in better than ever, and today we are modeling using sine functions, listening to the classic rock band ZZ Top, Give Me All Your Lovin', coming from the hot new CD, Dave's Faves, produced by the impeccable, unbelievable Miss Darby Foster. Let's get to it, shall we? Okay, so this is really good stuff. We are going to model some data using a sine function. And what does model mean? Well, what model means is, given a set of data, let's come up with a function which we can graph that will model or in layman's terms, go through or come close to going through all of these points, because then we can use that model to predict future behavior. That's exactly what we're going to do. And sine waves occur quite often in natural phenomena, in tides, I think they say up here, and sometimes in temperature, biological and physical phenomena. So right here, we have the mean monthly maximum temperature for Cape Town over a 12-month period. This is actual data. And the graph over a 2-year period is shown. So this data right here is just January through December right here. And then they graphed some more data but didn't provide the table. That's okay. We're just going to use the table and the first set of data to model our function. So give us some room to work here. And we're going to attempt to model the data using the sine function. And as we know, general form of a sine function is a sine b x minus c plus d. But in this case, we got temperature on the vertical axis and time in months, t, on the horizontal axis. So we are trying to find, let me find my pen here, we need to find A, B, C, and D. So let's start with the easiest. Let's start with A, and that would be the amplitude. So let's think about this. The amplitude is halfway between the greatest point and the least point. It's well, it's not halfway. That's where you get the principal axis, but it will be the distance from the principal axis to either the maximum or the minimum. So we can find that by taking the amplitude. We can find the amplitude by taking a maximum point minus a minimum point and dividing it by 2. And as we use that, it'll make sense. So the maximum temperature we have, let's see, is 28, and the minimum is 15. So that's 28 minus 15 over 2. So that is equal to 13 over 2. Now let's think about that. The distance from the greatest to the least is 13. And remember, the principal axis cuts or divides the top and the bottom almost exactly in 2. On a sine function, it actually does. Real data, it'll come pretty close depending on the data. So this is equal to 6.5. So our amplitude, A, is approximately equal to 6.5. And I say approximately equal to because we're not quite sure if this is going to be a perfect sine curve or not. So the period, okay, well, the period, if you look, if we start January and we go back down, and what we're doing is we're looking for the next time it's at about this height, and that happens to be in January again, 12 months apart, right? You see that? Here's December, then January. So the period is equal to 12. Remember, period is equal to 2 pi over b. So if I replace p with 12, 12 equals 2 pi over b. So 12b equals 2 pi, which means that b is equal to 2 pi over 12 or pi over 6. Bam, we're on a roll. So we got A, we got B. So let's take a look at D real quick, and then we'll worry about C. So D is the vertical shift, right? And remember, the vertical shift is equal, is the same thing as the principal axis, or the equation of the principal axis. Okay, so that is going to be the vertical shift, and in this case, we would only have to take it's midway between the maximum and the minimum, so it's the average of the maximum and the minimum. Do not get that confused with finding the amplitude. Okay, so the average of the maximum and the minimum, so D is going to be approximately equal to 28 plus 15, all divided by 2, which gives me about 21.5. Okay, and if you look on here on this scale, this graph here, if you think about 21.5 going through, you can see that it splits it in half almost. The top, the max and the min, the top and the bottom. Okay, and then finally we have to find C, which is the horizontal shift. And this takes it's not all that intuitive, but I think once you see this, you'll see that it's pretty easy. So let's just recall, okay, our basic sine curve, right? It looks like this, starting at 0, okay? But if we shift it, I don't know, to the right a little bit, it might look like this, yes? And then this would, if we continued it forever and ever, it would look like that. So what happened here is blue graph shifted this far to the right to start the pink graph, if that makes sense. And if I can find that distance, that is the horizontal shift. So the moral of the story is I am looking for a spot where the cycle, the sine curve first starts. If we think of the sine curve starting at 0 when the function is equal to 0. So in this case, this is again for the basic current sine curve. The principal axis is the x-axis, which has the equation y equals 0. So it's where the curve first starts at the principal axis. Okay. In our case, the principal axis is y. Let me just write that down. Principal axis is y equals 21.5. So let's look and see where it hits the graph at about 21.5. So if we look here, 21.5, 21.5, it looks to me like about here, like about October, it hits it at 21.5. Also, if you look at our data, it has exactly 21.5, right? So how many months is that, right? See if I connect this, this is where the sine curve first starts at 0. It doesn't hit 0 when it first starts. Now it hits 0 somewhere between here and here, but it doesn't start its upward turn until month number 10. So that means that the horizontal shift is this distance, which in this case is the 10th month of October, or 10. So we can now say C is equal to 10, which means we finally can write an equation that should model this data or come pretty darn close. So T would be equal to A, which we found to be 6.5, times the sine of B, which we found to be pi over 6, times B, which is, oh no, we found the B, sorry, times little t, minus C, which we just found to be 10, plus D, which is 21.5. Okay, and the only way to check and see how well we did is to go ahead and graph this puppy. So I have taken the liberty of plotting this on my TI Inspire. Now it doesn't look exactly like it, but I couldn't get it to thin out to look exactly like this graph right here. Let me back up so we get a better picture like this. But I think you can see it looks close enough. Now, this is 2 years worth of data, so look at what I did. This is month 1, month 2, so January, February, March, April, May, blah, 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 blah. December, right here. So I had to make 13 January for the second year. 14 would be February for the second year, and so on, the 13th month and the 14th month. All right, so remember that our prediction or our model, we think, is 6.5 sine pi over 6 t minus 10 plus 21.5. So I'm going to put that in there and see how it fits. So I need to analyze, and I'm going to plot a function. So I need to put in 6.5 times the sine of b, which we said is pi over 6, times x minus c, which is 10, plus d, which we said is 21.5, and let's see how we do. Not bad at all, sports fans, not bad at all. You can see how it's a pretty darn nice model of the data. It goes through a whole heck of a lot of points, misses this one, but it's generally a sine curve. And there's ways to make that even better, to get a better model for the data, but you can see how a sine curve could do a very decent prediction of the temperature for a particular month. For example, we could say, okay, what's the temperature going to be about what it's going to be in, I don't know, let's see, here's October, then November, maybe halfway through November, we could go up and find the y value when x is equal to 11.5, and you could predict the temperature in that manner. So there you go. Hope you enjoyed it. I know I did. Let's go back out from with some ZZ Top, and with that, I am out.